And let's talk about durability. Durability, in a nutshell, is the process of persisting the writes that clients make to the database to a non-volatile storage system. That means anything that we write is stored. So that means even if I lost power, or even if I crashed as a client after my committing the transaction, if I come back, I see that change. If the database crashed after the commit, I restart the database, I see that change. I see it persisted in disk. If my computer crashed, I come back, I see this change. That's what durability is. And you might think of that as okay, of course, everything is durable. Not really. A lot of database systems actually play with that. They play with the durability. It says, okay, durability is slow, right? Because to make things durable, that means you have to persist them to disk, and disks are inherently slow. So a lot of databases play around this durability and say, okay, I'm going to write my stuff to memory, and occasionally on the background, I'm going to snapshot and write to disk. So I'm going to make my writes faster. Can you get the database that does that? Redis does that, right? As an option, obviously, right? But durability is one of the strong relational databases must have, right? You have to be durable, right? And we're going to define what that means, really. So durability, changes made by a committed transaction, emphasis on committed, has to be committed. If it's not committed, really all bets are off. Must be persisted in a durable, non-volatile storage like SSD or hard drive. Durability techniques. There are many durability techniques. There is the WAL, the write-ahead log, which really, when I show you all these tables and indexes and stuff like that, these are really the representation of the data, which is what people read, what clients read. But these are really large if you think about it. So if you really write these things to disk, which we will, durability, committing a transaction takes time, because this is huge. These data and the data structures and the B trees and stuff like that, it takes time. So what databases implement is a version of the changes that happen only, which is deltas effectively. You can think of it as deltas. And then this is a write-only write-ahead log, which calls WAL. Any changes goes to this immediately first. We flush it immediately to disk. And this guarantees persistence. So yeah, we didn't really update the data table, right, on another data structure yet, but we can, if we have a crash, we have this beautiful WAL, we can go back and read all the WAL entries and then rebuild this state effectively, easily from a persisted state. We still persist this, we still write this durable, right, to disk, like the actual table itself, the changes, but we don't rely on that because that could be slow. And there's the another approach, which is asynchronous snapshots, or even synchronous snapshot for that matter, where as we write, we keep everything in memory, but then asynchronously on the background, we snapshot everything to disk at once. And that is also another concept. Redis uses actually both of these things. Append only file is another option, which is very similar to the WAL, really, that Redis uses, right? Which is keeps tracks of the changes of what happens and then writes these things. This guarantees that we have a very, lightweight way of storing data in a very fast way, but also in case of a crash, I can always read back and construct the state of the table completely without the need of storing the likes and the ID and the string and the blob and all that stuff, right? We store only these changes, and eventually we're gonna write that as well. So let's talk about the WAL a little bit. Writing a lot of data to disk is expensive, as I talked about that a little bit. We have indexes, we have data files, we have columns, we have rows, we have system files, system tables, all this stuff. If you imagine writing all the changes and the amplification of the writes itself, that's going to take a long time. You can do it, but it's going to be slow. So we need a better way. We need a more optimized, compact way. So they compress this version of these changes known as WAL, write ahead log segments. So they only write these log segment, and this this better be persisted, because this is what tells us what to change effectively, right? So these are just tells, hey, we changed this value to this, we changed this value to this, we changed this value to this, and we even compress that, so we get it in a very tiny segments. So there's something very critical in database systems, and this is one of the problems that operating systems do, and this is called the OS cache. When you actually write to the OS, you ask the operating system, whatever this, Windows or Linux. When the database asks something to ask the OS to write to disk, the OS actually does something shady. It writes not to disk, it writes to its own memory cache, right? And the reason is because it want to batch these writes and flush it to disk at once for performance reasons, because most applications does a lot of writes, and they want to kind of batch these writes and do it once. So because if you batch it, you do less IO, and if you do less IO, as I always talk about, this IO is better. But what's the problem with that? What if you say commit, and the database asks the OS to write the WAL segments to the disk, but the OS, they say, hey, I'm going to write it to the cache instead. The OS will tell the database that, hey, I wrote successfully, despite it only wrote to the cache. It didn't write to the disk. It will tell the database that, hey, database, or the application, it doesn't know it's a database, just knows it's an application that asks it to write something. And it will ask the database, hey, by the way, I'm the OS, and I wrote your changes successfully, but it only wrote it to the cache. So the database will say, okay, sure. The database will say, your transaction committed successfully. But the problem is, what if you get a crash there? The database told us it committed successfully. You get a crash, your computer will crash, you restart, and then the OS, obviously, the data was in the cache, on the OS cache. When you restart, it was in the RAM, obviously, so we lost the data, and as a result, the database lied to us. The database in that particular situation is not durable, because you wrote the transaction, because the transaction told us it was committed, but it wasn't durable. Why? Because of the OS problem here. So when the writes go to the OS and the OS crashes, machine restart could lead to loss of the data. And that's a big problem that databases fight for. So there is this command that bypasses the OS cache and asks the database, ask the operating system, hey, you dumb OS, I don't trust you. I tell you to flush these WAL changes, flush them directly to the disk. This is called the fsync command. So fsync command just forces the write always to this. So it's going to be slow. It's going to be very, very slow. So we have to do it with in a smart way, because you're bypassing the OS cache. And you might say, why this the OS uses the cache, right? Isn't it dangerous? Well, most of the situations, like, you don't really get a crash that often. So if you save a Word file or a notepad or something, things like that, it's okay to use the OS cache. Most of the applications use the OS cache, and it's very rare that this crash can happen. Database systems are different. They want to guarantee durability, and as a result, they have to bypass the OS cache. And as a result, it becomes slow. You see the trade-off, guys, right? There is always a trade-off. So fsync can be expensive and slow down commits, right? This is another problem, right? If you commit, you want to commit as fast as possible. So let's summarize the final lecture here. Durability is the ability to persist the changes when the transaction commits. The emphasis on the when transaction commits. So when the transaction commits, I want you to persist it on disk. I don't care. I don't care where you persist it. Here's what I want. When you tell me it's commit, I can shut off the power at that exact moment. And when I come back, my data better be there. That's what durability means. I don't care. You're gonna store it on the disk, on SSD, on the storage, on I don't know, in the air, who cares? I don't care. I want my data back. That's what durability is. A lot of databases play trade-off with these properties because durability is slows writes down, because now I'm going through this physical medium to process my changes, right? And as a result, it will be slower than if you wrote to memory. So Redis, for example, plays some games with that. It gives you option, actually, that none of the databases that I know of, even relational, gives you that option. Because guess what? It gives you the option. It says, hey, you want to be completely durable, strongly durable, or you want to be partially durable? Not even partial. Partial is the wrong word. Eventually durable. I guess I just made up that word. But eventually it's going to persist to disk. So there is a slight few seconds delay that if you lose power or if you crash, you could lose your data. Some people trade that off, that 3 seconds, with fast writes, because hey, I'd rather get fast writes, and okay, my data is not that important. I'm storing just logs of my application IoT devices. So who cares if I lose a few things? But guess what? Redis, most of the time, nobody reports loss, right? Because crashes are very rare if you think about it. When it comes to the actual databases, those guys build the systems to not really crash. But you cannot take that guarantee, because if Morphe is low, right? It says if it never happened, it will eventually happen, right? All right, guys, that was the last lecture of this. We're going to jump into many other lectures. I'm going to talk about eventual consistency. I'm going to show you examples here. So go with another lecture. It's called Acid Example by Practice, I believe. That's what I called it. And see how I do this in real time with the actual database. Show you all these beautiful properties. I'm going to also talk about eventual consistency, and I'm going to take a stab at the quiz and enjoy the rest of the course. Thank you so much. Goodbye.